Okay, greetings students, this is video number 1 for the module DYN3701. This video will give the solution to question 1 in test number 2. The question reads as follows: consider a cantilever beam AB with a constant flexural rigidity EI, with a Young's modulus of elasticity E and a moment of inertia I, that is rigidly mounted to a wall on one side at point A, its left side, and where the other end at point B, its right side, is hanging freely. The beam has a total length L, and the geometry is such that an upwards vertical reaction VA and a moment reaction MA is present at point A, where the beam is fastened to the wall, whilst there are no reactions at point B, and that's it. Recall that the standard sign convention is that x is positive towards the right, y is positive upwards, and the angle theta is positive in the counterclockwise direction, so that the beam has a positive bending moment if compression is in the upper part of the beam. For this geometry, utilize a coordinate system such that x is greater than or equal to 0, less than or equal to L, and let xa equal to 0 and xb equal to L. In this beam, a constant, uniformly distributed load Q is applied on top of the beam across its entire length, so that the beam deflects in a downwards direction, where zero deflection of delta A and a zero slope theta A are present at x is equal to xa, and a maximum deflection delta B and a maximum slope theta P are present at x is equal to xb. For the above statically determinate beam problem, determine the most correct expression for the bending moment m as a function of the distance x along the beam, taking into account the standard sign convention for bending moments such that m is positive when compression is produced on the top part of the beam. And then you effectively have to decide which of these formulae are correct for the bending moment expression. Right. Okay, let's do some calculations for question 1. First things first, let's draw the diagram for the system. There's a beam, AB. It's fixed at a wall on its left side. There is a UDL across the length of the beam. Okay, that's the geometry of the problem, and using that geometry we then have to decide which is the correct expression for the bending moment. Okay, let's write the options in a more convenient notation. Reading through the notations, we've got Okay. So we have to decide which of the options A, B, C, and D is correct. We could look through the textbook and find the formula. That's a valid option. This is an open book test. So we go through the textbook. We open the book. It's chapter 9. Chapter 9 is deflections of beams. Flip through the book and look for a similar problem. Right, and here we go. The problem is over there in example 9, over there. There's a simple beam, cantilever, a UDL on the top, fixed on the left hand side, and that it is, and that's the answer. So the textbook formula gives the expression for the bending moment as m is equal to minus QL squared over 2 plus QLX minus QX squared over 2. That's the formula, and referring to the options A, B, C, D, comparing the terms, the correct answer would be option A. And that is the end of question 1. If we couldn't find the formula in the textbook, we could derive it directly from first principles. The question states that the beam is statically determinant. If it's statically determinant, that means there's an equilibrium of forces and moments, and there's an equal number of unknowns and equations. So we'll talk about the statically indeterminate system in a later test in this module. But for now, the question is only for 5 marks. We could just easily look at the formula in the textbook and pick the correct answer. We'd get the 5 marks, 10% of the test. Alright, let's suppose we couldn't find it. We would then take equilibrium of vertical forces is equal to 0. Equilibrium of vertical forces, sum of moments at point A is 0. Using the sign convention specified in the equation, in the question. Using that sign convention, take a cut at some point x. Some point x between 0 and L, doesn't have to be half L. Take the cut over there, check what is on the left hand side of the cut and what is on the right hand side of the cut. This is the cut. This is a diagram. This is on the left of the cut, this is on the right of the cut. We can choose either direction to apply equilibrium of moments. Let's choose the left hand side cut. On the left hand side cut, positive bending moments is on the anti-clockwise direction, positive shear forces is in the downwards direction, vice versa on the other side. These are opposite, so the sign convention is important. So we would take equilibrium of moments, sum of moments at point x is equal to 0. Isolate what is the moments acting. There is the moment within the beam. The shear force doesn't contribute. The reaction force causes a clockwise bending moment, which is in opposite direction to the positive bending moment. Therefore this would be negative. And the reaction moment on the point A would be present. It will travel across the beam in an anti-clockwise direction, accounting for the sign convention which we assumed was positive. Apply the equilibrium of moments. M is positive. Shear force doesn't contribute anything. The reaction force contributes a clockwise moment, which would then be negative. The reaction moment would be anti-clockwise, which would then be positive because it's in the same direction. And then the UDL on the beam would be concentrated in the middle portion for the length x, and it will be a distance of half x, and it will be in an anti-clockwise direction, which is the same as the direction of the positive m. So we then add the force times the distance would equal to that. We would then solve this expression for the bending moment, which would imply m is equal to Vax minus ma minus a half qx squared. And we previously solved for the reaction force, the reaction moment. We substituted back into the expression. That would then be qlx minus a half ql squared minus a half qx. That's the answer from first principles. Looking at the options, minus ql squared over 2 minus ql squared over 2 qlx minus qx squared over 2 minus qx squared. Therefore, the correct answer would be option A. So the answer is m of x is equal to minus a half ql squared plus qlx minus a half qx squared. And that is the answer for question 1.